What is up, guys? Welcome back. Don't panic if you're just seeing all of this right now. We did all of this in the last page, so we're actually going to do the second page quickly and continue filling out the, Reteach review bubble where like web everything together. So, and the next thing really in this page is like beginning of triangle similarity. So there's like triangle congruence, and then I'm gonna draw a line in the sand. All right. So triangle congruence is awesome for us. We love knowing when shapes are equal, when shapes are the same, because we can tell when they're slightly different. And a way that they could be slightly different is triangle similarity. So very closely related to congruence, but not quite the same, is triangle similarity. So triangle similarity is only concerned about same shape. So here I'm going to say same shape. Last video we figured out that meant it has the same angles. So we really want the same internal angles for the triangles. So that's something you could write here. You could say like same angles. And so if I was going to draw a picture of this, I would draw one triangle that looks like this, and then another triangle that's the same size, that's the same shape, but maybe a different size, like it's bigger. So these angles here would all be the same. This would be the basics of a similar triangle. These triangles would be similar. We use a little squiggle to say that. And then same thing, we also have a naming convention for this one, except it is like using the similarity. So we would say like here, this was ABC, and this was DEF. We would say triangle is, let's see, triangle ABC, and the order still matters. Same thing is similar to triangle DEF. Well, not P, DEF. So angle A and angle D would be the same. Angle B and angle E would be the same. Angle C and angle F would be the same, which is exactly like we see in our picture. So these two triangles are similar. They're the same side. They're the same shape, and in fact, they are dilations of one another. So one is a scaled version of another. So in a second, on the next page, we will finally see dilations of triangles, or like scaled up, scaled factor, or whatever. Today, in just a second, right now, we're going to be checking for proportionality. So whenever this happens, whenever you have similar triangles, you get proportionality, which is like being the same up to a scale factor. So like if you multiplied triangle ABC by some factor, you could get triangle DEF. That would be called the scale factor. So we'll say, maybe scale factors like related to that. So there's a scale factor tack on. And you guys remember we did that forever ago. We were like, K equals 2 or whatever is like an example of a scale factor. This triangle gets doubled, so it gets multiplied by K equals 2. All right. Anyways, with this in mind, we can begin actually like using similar triangles on this next review page. So the next review page says, all right, if triangle PIG is similar to triangle ELT, and this is definitely a capital I because points names are always capital in geometry. So this is definitely a capital I. It says triangle PIG is similar to triangle ELT. All right. Identify the correct proportionality statement. So we want to identify a correct proportionality statement. So the way we can do this is by using the corresponding sides of the triangle. So in our example over here, when we drew this picture, we see that AB and DE, this would be the side scaled up by 2, just like BC scaled up by 2 is EF, AC scaled up by 2 is DF. And I mean, maybe not exactly 2, but you get it. In this case, we could use the naming to tell us exactly what's going on. So if, for example, PI should go with EL. PI should go with EL in its proportionality statement. Here we see there's only 2 examples that have PI and EL together, because since these guys are being, scaled up. And actually, a better way to do this, maybe just to redraw it. Let's do triangle PIG, just like we did on the back of the, just like we did on the previous page for the first question. All right, I thought I had more paper there, so it's going to be off the page a little bit. And then here we have ELT. All right. We could spell piglet with this. What? Okay, so in this case, we have P is going to be scaled up to EL. GI will be scaled up to this guy, and then this guy will be scaled up to this guy. So we see that PI and EL should go together is basically what I'm trying to say. So since these guys don't have that, we could cross those off. It's multiple choice. Let's use it to our advantage. It's multiple choice. Let's cross off the answers we know are not correct. So the next one, IG and LT should go together. IG and LT should go together. Beautiful. Okay. We see both of these also have that. Interesting. So for the last thing, we see that PG and ET should go together. All right. Oh, I'm sorry. And here we see P, instead of PG, we say GP, and here we see TE. That's the same. So maybe I should write, just as a note, remember that this is the same as PG, and this is the same as ET, but from the segment addition postulate forever ago. I mean, I don't even know if that's a segment. That may just be like an axiom of geometry. Yeah, it's an axiom. That's crazy. So, and yeah, so same thing, you know, we know that's true. And then here, we see that this one agrees, but this one says EL again. EL is repeated, so EL can't correspond to two different sides of the triangle. So here we'll say C should be the correct answer. Okay. Now, what this actually says, if you took the length of PI and divided it by the length of PL, it would be the same as if you did it with all the other sides. That is good because that means the triangle stayed the same shape after it was multiplied up. So in this case, if somehow, whenever you did the proportion, whenever you multiplied these sides by 2, if you had to multiply by a different number to get EF, the triangle would be wonky. It would blow up and be the wrong shape. And so for them to be the same shape, the proportionality has to hold for every side. So here we will say something like this, proportionality for all sides. I would say set up a proportion. A is to B, as C is to D, as E is to F. You know, I'm just picking random letters there, not like the lengths of any particular sides, but, you know. And then here we will see, on the next piece, we can try this out. We can actually test, we can see if this is true. We can test this proportion to see if triangles are actually similar. So, let's see. Here we could say, and the best way to do this is, like let's say, for example, so let's just take a look at it. Anyways, determine if the two triangles are similar. Show all work proportions. Give a similarity statement if they are similar. So the similarity statement is like what we saw earlier. That's the naming convention. This is the similarity statement. Maybe we should write that. Similarity statement. Sorry, my hand is right next to the camera, so it's really hard to write that way. Similarity statement. And here, we would like for the proportion to work out to get similar. So, if we say, for example, compared 30 to 12, we would be comparing the largest side of this triangle with the smallest side of this triangle. And then if we continued on and did, like, you know, compared it, is it equal to 27 and 18, all of a sudden we're comparing, 27 to 20, all of a sudden we're comparing the middle side to the largest side of this triangle. So if we compare the biggest to smallest and then middle to largest, our proportion definitely will not work. When you divide them, it definitely will not function. So if we want to give these the best chance of succeeding, we should do biggest to biggest, medium to medium, small to small. So we'll say big to big. Is that equal? And really, I'm writing equal, but I'm just testing it. We're just testing to see if it's equal. Is 30 over 20 equal to 27 over 18? And is that equal to 18 over 12? And in fact, we see that 30 over 20, that's the same as 3 halves. 27 over 18, that's the same as 3 halves. They're all the same as 3 halves. So I would say yes and yes. They're all 3 halves, so they're all equal. So this would mean yes, they're similar, and now we should write a similarity statement. So let's say triangle, and then how do we walk across the triangle? Well, if we start at M, we're starting at the mid, between the middle side and the largest side. So here's middle and largest side. That'd be this point here. So M should go with P. So M is similar to triangle P. All right, and then if we walked across the longest side, we would be walking across 20 to I. So it's been, you guys can see it's been rotated a little bit. So we'll go from A, and that should go with I. And then here we see the final letter would be R and T. All right. That's our similarity statement from this guy. And if we continue on, we could try another method. Now, we said you are definitely similar. Earlier we said the reason you're similar is if all your angles are the same. From this, a way to show proportionality, we'll see in a second. You can show these using proportionality theorems. So I'm going to shorten it to prop theorems because I'm running out of space right there. Proportionality theorems, and don't worry, there's only three. We had angle, angle. If any two angles were the same, then the third one also has to be the same, so they would be similar. And then we also had side, 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 which is what we just used, actually. And then we had side, angle, side. So these are three forms of similarity for triangles we can use to show proportionality. So in this case, I already see we have an angle in common between these two triangles, and I would like to know if this last angle is in common with the remainder over here. So what I might do, if these triangles are similar, this guy should be 60. So to test it, I will add 50 to 70. Let's see, 50 plus 70, that is 120. And then the remaining angle must be indeed 180 minus 120 is definitely 60. So this guy would be 60. And since 60 and 60 are in common, and 50 and 50 are in common, you could say these guys are similar by angle, angle. So we could say, let's see, triangle, in this case, we're start with B and E, both have the same angle. So we'll say B is similar to triangle E over here. And then here we'll have I and K, I'm sorry, is that, yeah, it's R. I and R go together. And then finally we have G is similar to D. All right. So for the next one, in these sets of problems, we will name the actual theorem of use and try and justify it along the way. So with these, we see, now A is a really tricky problem. So if you get this one wrong, do not feel bad. But what we see here is there's only three ways to prove something similar. Angle, angle, side, and side, side, side. So the problem with this is that this side and this side, you guys can see they wedge the angle here in the middle, but 15 and 10, the angle is nowhere to be seen between them. So this side, while it may correspond, so you guys can see 15 maybe probably corresponds to 6, 4 has no partner. So you cannot use side, angle, side. Okay. Likewise, since you're missing a side altogether, you cannot use side, side, side. Additionally, nothing can be known about these angles since no information is given that the lines are parallel or anything like that. So in that case, there's no way to show it's angle, angle either. Now, these triangles could be similar. They could not be. We don't know. Probably the best way is to say, like the best answer would be that this is an ambiguous case. The ambiguous case. There is no true answer. We can't prove it one way or the other. If you tried, try your best. Try if you may. I don't think there is a solution. If you find one, let me know. In this case, we're right back to angle, angle. Now, the reason I know this is angle, angle is there's no information about the sides of these triangles. No lengths are given. So we have to use angle, angle. So the only way I'm going to be able to test if this is actually similar is by checking. And here I see we actually have a 74 in common. So this side, if it really is truly similar, would have to be 65. Or I should say this angle would have to be 65. So let's see, 74 plus 41. That comes out to be 115. And then we can do 180 minus 115. And lo and behold, we get 65. So 65 can go right here. And since this angle is shared and this angle is shared, we see that these two pieces correspond. We can write our similarity statement. These guys are similar by angle, angle maybe. We say by angle, angle similarity. These triangles are similar. Let's see, starting at 65, we have P. Then we can go to 74. That would be PGI is similar to triangle. And let's see, it would be TSY. All right. For these last two on this page, we are applying what we know about proportional triangles. So we basically get to assume these triangles are similar here on the bottom. We get to assume these triangles are similar. Now, to show this, you would say, here's an angle they have in common, and then look, aren't these corresponding angles? So the triangles are definitely similar by angle. So we can use a proportion to solve for x and y. Here we see 4, 6 should be the same ratio. 4 to 6 should be the same ratio as 8 is to x. And in this case, if 4 is to 6, that would make 2/3. So 8 to x would have to be 12. So we could say x is 12. If you don't know, just cross multiply and divide, no problems. Same thing here, we can have 4 and 6 is equal to, and then to find y, it would have to correspond to this side. So 10 is to y. Here, if this makes 2/3, then to get 10 with 2/3, to get 10 over something to be 2/3, y would have to be 15. All right, and that's all you do for those. This is setting up the proportion is probably the hardest part, so focus on that whenever you get into it. So maybe we'll write that down over here. And then, like, connecting this, we'll say set up those proportions. Here, these guys are parallel, so it's by the same thing. This is a reflexively true angle for both those triangles, and then we have a corresponding angles down here. These triangles are definitely similar, therefore we could use proportions to solve them. So in this case, we see 2x and 5 and 6 and 3. It should be that 6 is to 3 by proportion, right? 6 should be to 3 as 2x is to 5. All right, and now we'll cross multiply to get 3 times 2x is equal to 6 times 5, which is 30. 3 times 2x is 6x, which is equal to 30. And then, of course, dividing both sides by 6, we get x must be 5. All right, that is all for this page. I will see you guys on the next one.